So let's get the EMF in this problem for the problem of the rotating rod using this rule, the V wire cross B dot ds rule. And so we put the rod on a rail. So this is a rail, this is a conducting rail, and it's fixed in space, it doesn't move. And as this rod then rotates, it's touching the rail, so that means it encloses some area here. And as the rod moves, this area gets bigger and bigger, and then we can start to talk about getting the EMF this way, and also by getting the EMF using the rate of change of magnetic flux. So first we'll do it this way, and then we'll get it using the rate of change of magnetic flux. So the ds vectors, we're going to go around the loop this way. So these are the ds vectors. And the velocity of the wire, remember, for a rod that's rotating, the velocity gets bigger as you go to larger distances away. What is V wire cross B? What's the direction of this? If you take the V and you take the cross product of V with the magnetic field, which direction does that point in? It points this way. Okay? So we want to get integration of V wire cross B dot ds. Now, the tricky thing here is how to deal with this ds. Remember, if you put an element of length, we're going to define then this axis to be the r axis, and the unit vector pointing in this direction, r hat, is the unit vector for this axis. Imagine if you want this to be the x-axis, we can just define this to be the x-axis. In this case, the r hat would be I hat, and then any point here would be located at a position x by position x. And how do we write the element of length in general? The element of length in general is always dxi plus dyj plus dzk, right? So in this case, it would be dxi. And I'm just using here dr instead of dx and r hat instead of I hat. So it'll be dr r hat. So that's the element of length. And remember, we let the limits determine the sign. We always put this the same. We always put this same in all the problems, and then we let the limits determine the sign. So if this point is not clear, you can come and ask about it, or ask in the comments. So the only part that's moving is the rotating rod. This is fixed, this is fixed. So the only part that's rotating, that's moving, has a velocity, is this part. So that's why we're integrating from 1 to 2, from this point to this point. So what's the dot product between V wire cross B, which has this in this direction, and r hat? The angle between them is 180 degrees, so you get a minus sign. So you get the magnitude of the first, magnitude of the second, times minus 1. Okay, so you have then the minus sign outside, and then you have integration. The magnitude of V wire cross B is V wire B times sine 90, which is 1, so it's just V wire B. And then the magnetic field is uniform, so it's the same. I can take it outside of the integration, but V is not all the same. Remember, V is equal to omega r, if you watched the previous video. So we can substitute V as omega r, and we can take the omega and B out, and we're left with integration of r dr. Integration of r dr is over 2, and then you substitute the upper limit, which is 0.2, and the lower limit, which is 0.1, and you get 0 minus L squared over 2. The minus and minus will cancel. Get the EMF is 1/2 omega B L squared. And it's exactly the same value we got for the potential difference across the rod between 0.2 and 1.